Hello everyone, I am Sai Karthik and a graduate student at Concord University working in the Complexity Lab of Building Civil and Environmental Engineering Department. Through this pre-recorded presentation, I will be speaking about advancing circular economy in the built environment, a framework for user-centered software tool development. Over the next few slides, I will talk about user-centered needs that must be considered while designing a software tool and to what extent does the existing software tools intended for rapid material inventory meet these requirements. To provide some background, the built environment generated 4 million tons of construction, renovation, and demolition waste. However, only 16% of this waste was diverted from landfills to recycling and reuse practices. Circular economy offers a solution to prevent this waste from ending up in landfills. But to implement any circular economy practices, knowledge of the material and component stock is essential. Unfortunately, this information for existing buildings is often non-available or incomplete. To address this issue, software tools that rapidly and accurately estimate material quantities of existing buildings are being developed, effectively transferring frameworks devised in research to industry. However, it is not enough that a software has only technical functionalities. A tool that only estimates the material and component stock may offer limited value in gaining adoption by the industry users. When two tools have identical capabilities are presented, the one that better addresses user needs and minimizes workload is preferred. Given the construction industry's inherent reluctance to adopt new digital tools, it is not a surprise that user interface functionalities are lagging behind other industries. This highlights the need to evaluate existing software to better design the future tools. The goal of this study is to develop an evaluation framework to guide the development of user-friendly software tools that perform rapid material inventorying of built facilities. This goal is achieved through two objectives. One, identifying and understanding the user-centered features that enhance software adoption. And two, evaluating the capabilities and limitations of commercial software that inventory materials in existing buildings based on their alignment with the predefined criteria. As a starting point, the criteria used to evaluate LCA tools for early design stages were considered. This criteria was then refined to suit the specific context of fast quantity takeoff for built facilities through a review of articles on digital technologies for the circular economy. This led to a revised framework with four themes: input, analysis, output, and user interface or user experience layer. Then a list of software for automated quantity takeoff was compiled and filtered based on the following criteria. They focus on built facilities, generate material composition as a primary function, granularity is at the building level or lower, do not require detailed as-built drawings or 3D digital models, and are not BIM software plugins or add-ons. Finally, the alignment of identified software with defined user requirements was analyzed. A total of 17 criteria were identified, 3 under inputs layer which define data input and their corresponding import mechanisms, 5 under analysis which define requirements related to transparency in calculation methods and expected outcomes, 2 under outputs layer addressing how results are presented to the users, and 7 under user interface or user experience layer covering requirements that enhance tool usability. Under the inputs layer, the first requirement is that the information required from user should be minimal. The second requirement is that the software should integrate into users' organizations with minimal need for new infrastructure. The third requirement is that data input process should be scalable, that is, handle multiple data streams. For example, a single Excel or CSV file containing information of multiple buildings or projects should work fine. Under the output layer, the first requirement is results should be presented in an easy to understand format such as graphs, pie charts, etc. The second requirement is exporting results as a document should be possible with an ability to customize the content of the document. In the analysis theme, users favor transparency concerning how the material quantities are calculated. Next key requirement is fast calculation, which in the current context implies minimal runtime to generate results. The tool's acceptance is also affected by its ability to support decision making through evaluation of alternate disposal scenarios and the associated financial analysis. If a software uses machine learning for generating results, it should support continuous training of machine learning models on the expanded data set. The criteria under user interface or user experience theme are general in nature. Since the material quantities generated by the software tools are not always accurate, it should allow users to modify quantities and specifications when inaccuracies are identified in later project stages. The tool should be adaptable enough to support extended functions as the project advances, which for the circular economy means support for deconstruction scheduling, inbuilt material transport generation, etc. The requirements, which are general in nature, include data preservation to prevent loss of project information, user documentation and floating tool tips for tool use and troubleshooting, sufficiently simple enough interface for easy learning. Another key requirement is interoperability with external tools such as GIS to query a building's location, integrating results with external material passport generators. If the software utilizes machine learning to estimate material quantities, the tool may also include a predefined template that enables users to convert completed projects into new data points for model improvement. After performing the search and applying the filtering criteria outlined in methodology, four software tools were identified. Domestic Waste Generation Rates Calculator for Metro Vancouver, EvalMetap short for Evaluation of Metabolism, Carbon Designer 3D tool for one-click LCA, and LCA BYG. The first three are web-based applications, while the LCA BYG is a desktop application. The first two focus on demolition waste, whereas the later two are primarily intended for whole building LCA. Only two tools, Domestic Waste Generation Rates Calculator for Metro Vancouver and LCA BYG, provide transparency in their calculation mechanisms. There is notable variation in the number of materials estimated. Demolition waste calculators are limited in scope in the number of materials they estimate, while the LCA tools are comprehensive but require manual effort to aggregate material data. All tools require relatively limited data input to generate results, with Carbon Designer 3D requiring the most inputs. In terms of alignment with the defined user requirements, in the input layer, only limited data input criterion is satisfied by all four tools. Within the analysis layer, fast calculation is supported across all four tools. Evaluation of metabolism stands out by also having alternative scenarios and financial analysis. The absence of these functionalities in Carbon Designer 3D and LCA BYG tools is expected, as they are not primarily designed for material inventory. In the outputs layer, all tools generally meet the two defined requirements. In the user interface layer, the tools focusing on demolition waste satisfy only two of the six criteria, whereas the LCA tools meet a greater number. However, taken together, no single tool satisfies more than half of the defined criteria. To paint an overall picture of the results, software tools for circular economy have standalone functionalities requiring multiple tools to handle different tasks as a project advances. Most circular economy tools focus on earlier stage LCA based decision making, and there is a need for tools that support decision making for existing buildings nearing end of life. Future tools should be robust, effective, comprehensive, and should be designed to meet the needs of stakeholders. This can be achieved by aligning future tools with earlier defined user-centered requirements. In conclusion, a gap remains in the availability of user-friendly software tools that enable rapid and affordable material inventorying of existing buildings. This study has contributed a user-centered design evaluation framework to guide the development of software tools to advance circular economy practices. The main limitation of this study is that the user-centered requirements are derived from published literature, reflecting the theoretical nature of the proposed framework. Future research will identify the requirements and technical functionalities considered critical and feasible by the industry stakeholders through surveys and interviews. Thank you for listening to me.